All right, let's get rolling here today. Welcome, everyone. Thank you for taking the time out of your day to join us. This is the Navigating the Heat Pump Jungle webinar. My name is Kendall Sewell. I'm a senior associate at SEEA, and I'm really excited to be here today to assist Brynn with this webinar. I have a couple housekeeping items to cover before we get started. Please note that this webinar is being recorded. If you have any questions, please submit them in the Q&A box below throughout the presentation, and our speaker will respond to those questions once he wraps up his presentation. So we'll save Q&A to the end. Following this webinar, we will send all registrants the recording and the slide deck, as well as any resources mentioned in the presentation. And there's also going to be a short survey immediately following the webinar. And please take the time to fill this out. I think it's about 4 questions, and we'd really appreciate your feedback. But before we get into the webinar, I, of course, need to plug SEEA for a moment. For those who don't know about SEEA or those who want a refresher, we are the Southeast Energy Efficiency Alliance, founded in 2007. SEEA promotes efficient energy as a catalyst for economic growth, workforce development, and energy security across 11 southeastern states. We provide research, consultation, and education, stakeholder facilitation, program management, and financial services to a range of stakeholders working in the energy sector. Our goal is to optimize the use and impact of energy so that all people in the Southeast can live and work in healthy and resilient buildings, utilize clean and affordable transportation, and thrive in a robust and equitable economy. Today, we're going to be talking about the best practices for installing heat pumps, and I have the pleasure of introducing our guest speaker, Brynn Cooksey. Brynn is affectionately known as the Air Doctor. He is a Detroit native and the owner of Air Doctors Heating and Cooling in HVAC-U. He is a renowned expert in HVAC-R, electrical, and building science, and has trained over 10,000 industry professionals. He's a certified master trainer with IREC. In 2004 and 2005, Brynn was named one of ESCO Institute's top 25 most influential HVAC-R instructors. This honor was given to instructors who significantly contributed to the HVAC-R industry. And as well, in 2024, Brynn was named one of the top 40 under 40 industry professionals by the Air Conditioning, Heating, and Refrigeration News. So Brynn continues to lead through innovation, education, and technical excellence. I'm personally so excited to learn from him today. So please join me in welcoming Brynn. I'm now going to turn it over to him to begin his presentation. Thank you.
Thank you, Kendall. Appreciate that. And before I get started, Kendall, can you see my screen okay?
I sure can.
Excellent. Well, good afternoon, everybody. Welcome to our presentation. Today, we're going to talk about navigating the heat pump jungle. Interesting topic. There's a lot of discussion about heat pumps. It's a really popular topic. So this presentation is going to give us kind of a 10,000-foot view on some of the best practices for program design, heat pump installation. So let's get started. Our objectives today, when we go through this presentation, we're going to talk about federal incentives, specifically the IRA, or what's left of it. We're going to talk about why heat pumps were selected. When we're looking at heat pumps, one of the challenges is properly sizing and selecting it. So we're going to go over some of the guidelines, and then we're going to go over heat pump best practices. Now, why do we call it a jungle? There's a lot of conflicting views and opinions out there, and without the proper research, the information can be sketchy at best. So, when we look at a jungle, we need to navigate it. We need to know and understand what exactly we need to do, especially if you're a utility company or implementation contractor and you're going to run a heat pump program. Maybe you are tasked with putting heat pumps in on a large scale. With that being said, let's navigate the jungle so you understand exactly what you should do for your program so that you have good customer outcomes. Now, why are we talking about heat pumps today? One of the big things is energy efficiency. So, if we look at the demographic of the US, the population, we're about 4% of the world's population, but we consume roughly 16% of the world's energy supplies, and this is from the U.S. Energy Administration. With that being said, for every dollar we put into our energy, we're only getting about 26 cents out of it. So that's including all energy sources. So as a result, here in our country, we have the unique problem of using energy inefficiently. So in 2022, the Inflation Reduction Act was passed into law, and basically $400 billion was set aside to incentivize, residences of the United States to basically use energy efficiency countermeasures to help reduce their carbon footprint and reduce their utility bills. Now, 8.8 was earmarked, and with current legislation that's in place, some of the IRA was repealed, but many states were able to get their money out the door. So, with that, we are still seeing some states have a viable plan to administer those IRA rebates. And as a result, heat pumps are a big focus. So, if you are looking at a heat pump or you're running a program, there are still tax credits available up until the end of this year, December 31st, 2025. If you're looking at an air source heat pump, you can get 30% of the project up to $2,000. If you get a furnace or air conditioner, that same tax credit that's going to expire will allow us to get 30% of the project up to $1,200. You can combine those rebates to get a max of $3,200 annually. And again, those expire December 31st. Now, when we look at the IRA, for those states that were able to get their programs launched and they were not clawed back, the heat pump is a critical part of the Homes and Here Act, specifically the Here. When we think about electrification, which we'll cover here in a little bit, there is some huge incentives from a climate standpoint due to less carbon emissions and indoor air quality. So heat pump adoption was incentivized. If you look here, the heat pump itself was allocated from the Department of Energy at $8,000. And we had supporting tests that we can do to support that heat pump for a grand total of $14,000 based on the customer's income level and where they live. So heat pumps were incentivized. Again, it's sketchy at best. Some states were able to get that money out the door and actually run their programs. Some states are still trying to get those programs launched. But the context of heat pumps, because of the efficiency of heat pumps, we're still going to see them have a massive marketplace share here in the future. Now, when we talk about heat pumps, they're the new buzz. Heat pumps are one of the only devices that can deliver more energy than they consume, which makes them extremely efficient and makes them ideal for reducing your utility bills and fighting climate emissions. But the technology isn't new. Heat pumps have been commercially available since the 1970s, and they've been available, but they were typically found or more prevalent in warmer climates, such as the southern, southeastern, southwestern, or western parts of the country. But they're not new. The technology has changed where heat pumps can deliver all or nearly all of their capacity at cold climates, making heat pumps a viable option anywhere you go in the country. Now, you might have heard this term electrification. What is electrification? Electrification, we're going to replace non electric appliances with electric appliances for the purpose of reducing carbon emissions, where we will supplant a furnace and add a heat pump. Maybe use a heat pump water heater to replace a conventional gas storage water heater, and maybe use a range or oven or a heat pump dryer to supplant older combustion appliances. As a result, it has been proven that those items will use less energy and you don't have the emissions of combustion, which can cause respiratory issues. Another part of electrification, which is secondary in scope, is to provide weatherization. So, looking at a building at home, weatherization includes adding attic insulation or doing air sealing. These things, when you do that to your home or business, reduce your energy consumption. Therefore, you are performing in electrification. So, using electricity is pretty important for us to go for electrification. when you talk to people, or I'll have conversation about electrification, one of the pushbacks that I get is I may have an individual say, "Are you just moving the smokestacks?" And that's a legitimate question. And what they mean by that, instead of me having my carbon emissions locally at my home or building, I'm just moving those carbon emissions to the power plant. Did I really do any benefit by doing that? And it's a really legitimate question. And the answer is yes, you are. And here's why. Electricity is highly regulated. We have all kind of third-party regulatory agencies that govern our utility companies. So it's highly scrutinized, and this a demand for it to be clean and reliable. But if we look at our combustion appliances in our home, if you don't have any issues, those appliances can go unchecked for decades. Very few places in the country require some kind of active combustion testing just to verify that those combustion appliances have proper emissions. And like we mentioned, heat pumps can be more than 100% efficient. They can deliver far more energy than they consume, which beats, say, a gas furnace that only can deliver 98% of its energy that's inputted. So heat pumps have some big benefits. What about carbon emissions? When we look at carbon emissions, many argue that replacing combustion appliances will move the smokestacks like we talked about. However, that heat pump can have 40 to 70% less of a footprint than a complementary furnace. So it's really important to look at the total scope, how the heat pump using electricity is a far more cleaner product, which will cause energy savings and reduce carbon emissions. Now, there's another strong opinion that the grid can't handle it. Um, there is an opinion that comes out that say heat pumps are going to challenge the grid, and that is a legitimate concern. And that grid is also a concern as far as data centers. So when we look at heat pumps, they are becoming more efficient and they can modulate their output capacity. So as a result, heat pumps will be the future. Another myth that we get into is that heat pumps don't work in cold climates. And that's also a myth. The traditional heat pumps, the heat pumps from yesteryear, they did have challenges operating in cold climates. Hence, that's why they were used in the warmer parts of the United States. As outside temperature drops for a heat pump, older heat pumps before cold climate technology, that heat pump capacity and efficiency dropped off with it. So it really didn't see rapid market adoption in the northern part of the country. And with colder climates, we had massive heating loads where our buildings required a lot of BTUs or energy to heat or cool them. And as a result, that massive heating load will eclipse even the biggest heat pump that we can put in. And we fix that now through projects such as weatherization. Now, if you're working in a program and you're working with clients, you have to provide some type of education. Um, with heat pumps, the way they operate, when I'm working with a furnace, I'm burning a fuel and I have really hot exhaust gases that exchange your energy with the circulating air. So, from a furnace standpoint, the air coming out of the registers is significantly warmer than it would be for a heat pump, which is simply moving heat from one place to another. So, prior to working with a customer that is going to utilize a heat pump, you have to prepare them for the differences that they're going to encounter. You may put in a heat pump for a customer not to understand that they're going to have some physical differences, only for them to complain that the air is not distributed properly or that the heat pump isn't working. Heat pump can be working fine. We just didn't set our customers' expectations properly. Now, we now have cold climate heat pumps. These cold climate heat pumps are awesome, and the fact that they can deliver all or nearly all of their capacity at really low temperatures. Some manufacturers even market that they can deliver all their capacity to really extreme temperatures like -22, where any part of the country we can use a cold climate heat pump to deliver comfort. One of the ways we're able to do that is through use of a inverter compressor operation. When we think about an inverter compressor, I want you to think about a device inside the heat pump that's able to precisely control the capacity of the heat pump based on the demand. So older heat pumps, they were fixed speed where they would turn on and turn off. Newer heat pumps, because we have the ability to control the compressor speed, we can modulate the output and in some cases even make the compressors run faster to deliver more output if needed. And that's just some technology that we did not have in the past. So these cold climate heat pumps are able to do what they're able to do through the use of a compressor. Now, before you dive into a heat pump project, you should really think about, before using a heat pump project, should I weatherize my building shell? Some people call this permanent load reduction. And what they'll do, they'll say, hey, I want to put a heat pump in, but I want to put in a smaller heat pump, maybe one that doesn't have as much capacity. Or if I tighten up my building shell by adding insulation, such as in the attic or wall, or doing air sealing, I'm going to reduce that load. Therefore, I can get a smaller heat pump, better energy savings, so on and so forth. So prior to using heat pump technology, you should ask yourself a question: should I weatherize prior to going all electric? Now, we have heard some horror stories about rapid heat pump adoption, and a lot of those horror stories come from the simple fact that when we were using forced air heating and cooling systems that use combustion appliances such as a furnace, that furnace has such a high delivery air temperature that it masks a lot of our design mistakes. Right. So you can have a furnace that wasn't sized properly, that was not commissioned properly, but just because it delivers such a warm air temperature to the space, oftentimes the customer still experiences a relative level of comfort. However, was it perfect? And the answer is no. What you see on your screen here now is ACA Manual J. This is a design standard for heating and cooling professionals, and this standard has been around for decades. However, its adoption is very poorly used. And what I mean by that, there's all kind of reports all over the place where as many as 50%, 60, some reports say 70% of the residential systems in America are improperly sized. We conducted a study here locally in Michigan and we surveyed about 3,800 homes. And when we looked at those 3,800 homes, 98% of them had oversized equipment. The furnaces themselves, when we did the survey, were oversized by 100% or more. And the air conditioners that were installed were oversized by 1 ton or more, which represents a number of issues: inefficiency, rapid starts and stops. It represents mechanical failures, breakdowns, and your bills will climb due to the inefficiency. So as a result, we have this problem. If you replace a heat pump for a combustion appliance and you don't do your good due diligence for design, you're going to set that customer up to have a bad outcome. When we look at Manual J, just at a high level, there's much deeper training, and if you're interested, you should dive into it. But what a Manual J process is, we're going to evaluate the building shell, and we want to see how much insulation does it have and how leaky the building shell is. And we're going to calculate the size of a heat pump to fit that structure. Okay? Your home does some pretty extraordinary things. One of them is called stack effect. As your home is residing right now, due to a difference in temperature between inside and outside, in the wintertime, air from outside will travel into the home, eventually get into the system, get into your heating and cooling system, get conditioned, and as it gets conditioned, it becomes less dense and it rises. When that air rises, it finds weak points in your building shell, such as an unvented attic, and you see these red arrows here, that conditioned air is going to leave out. So if you don't plan for this or fix it through weatherization and you improperly size a heat pump, you're going to set yourself up for discomfort, high utility bills, so on and so forth. Another thing to consider is the building properly insulated? older housing stock in my neck of the woods, Metro Detroit, we have houses from the 20s, and they don't have any insulation inside their walls, very little in their attic, if any. So as a result, this is going to change the demand or requirement for the size heat pump that needs to go there. So if you're running a program for heat pump adoption, you really need to make sure that your contractors or trade allies are performing load calculations. It's critical. If that load calculation isn't done, which accounts for the leakiness of the building shell and whether the shell has insulation or not, you are going to set yourself up for bad outcomes. Right? For best results, for the load calculation, you should conduct a blower door test. The blower door is a diagnostic tool that is going to pressurize or depressurize the house. And its goal is to try to quantify the building air leakage. This is important in a couple of different ways. Number one, if I know my building air leakage in, I can refine my load calc. I can make it that much more accurate. Number two, even if my heat pump is sized accordingly, if I have a building shell problem, that customer might experience discomfort in certain areas because of building leaks. And if I'm able to detect those, I can include that work into my work scope just to ensure that my customers are comfortable. So it's pretty important to run a blower door test. Now, a blower door test is a test that simulates a 15 to 20 mile per hour wind. Okay, when you run a blower door, the airflow hits the building at the surfaces, and it comes in through the gaps, cracks, and holes of the building shell. And the way it works, when I run a blower door, as the air is discharged out of the blower door, buildings have this relationship. If I take air out of the building, air has to come into the building. And as a result, I have a test pressure. That test pressure we rate in pascals, right? A pascal is roughly the weight of a post-it note, and there's 249 pascals in 1 inch of water column. Fairly small pressure when we're looking at it in the grand scheme of things, but it's pretty important to note that a blower door is simulating that wind pressure that's going to hit our building structure. When evaluating a blower door, we need to know a few definitions to understand how that blower door is working. Some of the terms that we're going to use for blower door testing includes the cubic foot per minute. I want you to think of cubic feet per minute as a basketball of air. Okay. And when we run a blower door, we're going to push basketballs of air out of the house through the blower door, and basketballs of air are going to come back through the gaps, cracks, and holes inside our building shell. When we see CFM subscript 50, this means that we ran a blower door test at a test pressure of 50 pascals. And that means that the CFM generated by the blower door was exaggerated by the blower door. That's where that 50 pascals come from. So CFM 50 is the standard for blower door testing. It gives me a way to test the same house multiple times and to evaluate if I did air sealing properly. It also gives me the ability to compare two houses. All right, if I test one house at one pressure and another house at another pressure, it's not the same test pressure. So CFM 50 is our blower door test pressure. When looking at the blower door, we have a blower door system or apparatus, which includes the fan, the frame that the shroud goes into, this manometer and pressure gauge, and the assortment of tubes and hoses. And when the blower door is being used, we have to pick a orifice or hole or opening in order to get the proper airflow out of that blower door. Blower doors are essential for evaluating if a home is going to be suitable for a heat pump install. If I have an excessively leaky house and I have an air seal, remember I don't have the backup of the muscle of the gas furnace. That gas furnace can put out really, really warm temperatures and it can hide building issues. That heat pump, even though it's physically capable to do the work, I don't have that muscle, I don't have that high temperature to support me. So if you put in a heat pump, part of your load calculation should include a blower door. When you're looking at the blower door, quite simply, you're putting together a frame. you're going to wrap a shroud around it. And when you wrap a shroud around it, you're going to install it and the fan inside the blower door, and you're going to operate some type of pressure gauge. Okay. This is the test pressure that we're looking at, our negative 50 pascals. And on the right here, we see that we have a flow at 50. Okay, flow at 50. That flow at 50 represents how many basketballs of air do I have going into and out of the house every minute. When we go to set the blower door up, we're going to set it up in any exterior door. We're going to put the house in wintertime conditions by closing all exterior doors outside of the one that we're using. We're going to disable our heating and cooling systems. We're going to close any fireplace dampers. We're going to extinguish any fires and maybe let them cool and cover the ashes with wet newspaper so we don't bring ashes back into our space. And we're going to run our blower door. And when we run our blower door is going to push air out of the building shell, and that air is going to come back through the gaps, cracks, and holes in our building shell, and our pressure gauge is going to help calculate how leaky that structure is. And it's pretty powerful and important. Let's take a look at the data that the blower door gives you. All right. So remember, blower doors are the readings are given in CFM 50, okay, cubic feet per minute, or basketball of air at 50 pascals. So if I had a CFM 50 of 5,000, if I'm able to take that cubic measurement to square inches and divide by 10, I can therefore visualize that this house that had a 5,000 CFM 50 had a rough opening of 500 square inches, right? Roughly an opening of 20 by 25. So I go to a house and I want to evaluate a heat pump. I put the blower door in and I get this number. If I divide it by 10, this is approximately all the leaks inside the building shell together are going to represent a hole from inside to outside that large. Okay. If I put a heat pump in and I don't evaluate that shell leakage, I could be setting my customer up for some bad outcomes. Maybe I need to weatherize my building shell by air sealing, making this hole smaller and adding insulation in the walls and attic. All right. So as you're running your programs, it's always important to remember there are no rules of thumb. There were tribal knowledge rules that were passed on from generation to generation in the skilled trades, and they are all inaccurate. Whenever you want to evaluate a building shell to install a heat pump, you should always, always, always perform a manual J calculation. All right, every building is different, and assumptions should be avoided. Let's take a look at an example. This is a load report of a home, and if you see in this home, I have a heating load of 107,000 BTUs. Okay, and I got a cooling load of 43,000 BTUs, so roughly a 3.5 ton air conditioner and a 107,000 furnace. This is pre-weatherization, so this was before I air seal and insulate. Let's look at what happens after I air seal and insulate just to the minimum code standard. Looking at my same house, all right, I drop my heating load to 39,000 BTUs, and I reduce my system from a 3.5 ton system to a 2.5 ton system. So before using a heat pump to provide conditioning, you may have to weatherize your building shell. That's pretty important. If you don't, the load may be so large that even if the heat pump can deliver it, your load may be bigger than what the biggest heat pump can deliver. Systems are often oversized. This is a load calc report that we've done with the customer. And if you see here, it's pretty small, but this customer had a furnace size that was 110,000 BTUs per hour. So if I try to replace that like for like with a heat pump, one, they don't make one that large, and then two, it would be a huge mistake to do that without doing a load count. This is a software report from an energy audit, and look at the heating load, and this is base. This is prior to me doing any kind of weatherization. All right, it's over half the capacity of the system before I do any weatherization. And after I do the weatherization, it drops down even more. So the bad habits of swapping equipment like for like, not evaluating the building shell and the building features, if you do that with a heat pump, you're going to run into some massive operational problems. Okay? When you properly size it, this is a tool that we use called Emerson eSaver. And it basically takes the fuel rates inside of your area and it leverages the existing system you're going from to the system you're going to. So if I was to go from a 100,000 BTU furnace to a 38,000 BTU furnace, these are fictitious. And the savings in a year due to properly sizing the fuel rates in this area from this calculation, it came up to about almost $1,200. So properly sizing the system, you can see will create less carbon emissions and it'll also reduce your bill by having it properly sized. Another consideration to look at heat pumps is the duct system. Is the duct system sized correctly? Like the load calc, we use another design standard called Manual D. Manual D is a residential duct design handbook, and this walks us through all the procedures to do duct design. That same survey of 3,800 homes, we found that 98% of the ducts were undersized by 100%. So not only were load calcs not done for these residences, the ducts were not evaluated either. And here's a problem. For the same reason of the load calc, if I put a heat pump and I don't evaluate the duct system, I can be setting myself up for issues also, especially when the ducts are located in an unconditioned space. If you have ducts in the attic or crawl space and they're not properly sealed, sized, and insulated properly, that low discharge temperature of the heat pump is going to be eaten by the heat loss to the ambient air. So as a result, you have even more homework to do when heat pumps are on the table for a customer. And the duct system should be evaluated to ensure that not only is the load sized properly, the ducts can handle often the additional amount of airflow needed for a heat pump. Common duct issues include improperly sized, not balanced, not sealed, not insulated. They were not clean. And from calculations we've made, an improper duct size that is mismatched to the equipment can typically cost a customer about $230 locally in our market, and that's per year. Now, how do we go about to resolve that? One of the things we do, we measure for airflow of the existing system to see that heat pumps are actually feasible in this location. And two things need to be true. Do I have a building shell that can accommodate a heat pump correctly? And do I have a duct system that I can measure, get the airflow requirements of the duct system, measure static pressure or bursting pressure of the duct system to see if a heat pump is the ideal candidate? Again, heat pumps are wonderful and they work everywhere, but there's a little bit more homework we have to do to have rapid heat pump adoption. When we look at duct systems, if they're in an unconditioned space, are they sealed? Right? Are they insulated? We need to take that all into account to do this before that heat pump goes in. Airflow is so prevalent in our contracting business, we linked it to um, critical failures like heat exchanger failures. What you're seeing now is a forced air furnace system that this is a crack. Right inside this apparatus or heat exchangers where the exhaust gases are going to go through our furnace and go up and out to the atmosphere. And due to poor duct design, this heat exchanger has failed. If I look here at this heat exchanger, this crack will allow exhaust gases to get into the people space. This was caused by inadequate airflow or improper duct design for our heating equipment. So again, if you don't do your due diligence on a design and you put a heat pump in, no, you're not going to have a combustion related failure, but you may damage the compressor or the main part of the heat pump outside. The third manual we need to look at for proper design is Manual S. Did we select the right equipment for our customers? There's guidance in ACA Manual S to help us identify the heat pumps, what size, the equipment selection to make sure that we select the right equipment for our application. Heat pumps are highly sensitive to improper size, poor duct design, and if we select the wrong equipment, it's going to be bad outcomes for customers. When we look at the typical cycle now for a contractor who hasn't been trained in building science, the cycle is for us to take the equipment, replace it because it has some type of catastrophic failure. If the contractor wasn't trained, they're going to put in the wrong size. The duct design was probably wrong because that wasn't a strong focus in many parts of the country. And the systems are often, due to several reports, not properly commissioned or balanced. And as a result, it's going to lock our customers into a cycle. So every 10 to 15 years, they're going to have a catastrophic failure. When they have that failure, they're going to get the system replaced. And if they don't do their due diligence as far as duct design and load calc and selection, they're just going to be locked into that circle and continue to have that problem. So, in order to break the cycle, we have to do our homework. Now, when you're designing heat pumps, there's three design approaches that you could take. The first design approach is the size of heat pump to the heating load without backup. Remember, the heat pumps can deliver all or nearly all of their capacity at very low temperatures. The technology is amazing. The second way is to use a heat pump, but have some type of supplemental or auxiliary heat where the heat pump makes up a large portion of the heating load, but I use a supplement like electric resistance heat to make up the difference. And then third, I have a backup source called dual fuel. Dual fuel is using a heat pump as your primary source and then using the opposite source, such as a backup gas furnace, to stand in when the heat pump is either tapped out as far as capacity or is too costly to run due to rates. So these are three design approaches that you can use. When sizing to the heat pump to the heating load, follow manual S guidance. The building shell should be well insulated and air sealed. And with this option, you have to remind customers that there's no redundancy. And oftentimes, because heat pumps require more airflow, you're going to have to do a duct modification. Where I live in Michigan, electricity is about 6 times more expensive than natural gas. So you have to warn your customers that even though they may physically be saving energy, like there's physically less BTUs being consumed due to the cost difference between one fuel to another, their bills may rise substantially. And that's something that the customer has to be prepared for. Some customers don't care and they want to be altruistic to fight climate change. But just imagine if you're surprised with a $1,500, $2,000 a month electric bill and you didn't know about it. You also may have to add supplemental dehumidification. If you're in I'll say, a cooling climate like Michigan is, we have more heating hours and cooling hours. Our heating loads are usually substantially larger than our cooling loads. And as a result, that heat pump, which is a two-way air conditioner, will be bigger than is needed. And if that's the case, I may not remove the moisture in the summertime. So I may need supplemental dehumidification. And according to Manual S, that number is 30%. Anytime my heating load to cooling load is bigger than 30%, supplemental dehumidification is required. Okay. If you don't have supplemental dehumidification and I can't control that humidity, I could get possible biological growth and issues with the building shell, such as durability issues. Our second method was talking about the heat pump size to the cooling load and maybe using some type of electric backup. Also costly, and many times this is going to require duct modification because heat pumps require more airflow than a traditional furnace. Um, as the heat pump capacity drops off if it gets really cold, what will happen, the supplemental heat will come on and supplement the heat pump. The intent is for the heaters and the heat pump to run simultaneously. All right, we're going to use a heat strip or heater bank to supplement that. Again, when you put this type of system in, the customer's bills may increase substantially and they need to be warned about it. When you do this type of setup, it may require a service change where the service that's for my customer's premises may be now inadequate to accommodate the heat pump. So I may have to increase that service to accommodate the heat pump and my electric heat strips. And my personal favorite is dual fuel. Dual fuel is a furnace heat pump combination where the heat pump is the primary source and either the heat pump taps out on capacity or if my savings is lost because of the temperature outside and the cost of my fuel, I can turn the heat pump off and bring on my gas bills. This is one of the best options because I can run electrification for a large amount of the time during the year and only rely on my gas furnace when it gets really cold or my rates are high. Duct modification may or may not be required depending on how you size it, but this is one of the ways where you can split the difference, have the backup of gas fuel, but also participate in electrification projects. And with that, we'll take some questions.
Thank you so much, Brynn. We appreciate your time and expertise today. As he said, we're going to move into the QA portion of this webinar. Please, I encourage you all to include your questions, whether they're more high level or more technical for Brynn today while we have him. Yeah, just drop them in that Q&A box and I'll be monitoring it. I'm happy to start things out because I've got a few questions for you, Brynn. The statistics you gave on how big of a problem oversizing is was pretty shocking to see. I guess I'm curious to know a bit more, like, in your opinion, what's needed to address this issue if it's affecting so much of the country? And then, yeah, it's a two-parter. So what do you think to that portion?
Sure. This is a personal opinion, Kendall.
Mm-hmm.
So I the design process really isn't a focus in many trade schools, just in my experience. So as a result, if they don't have the time or it's not a part of their curriculum, they may not get exposed to it. And then also for a contractor to go to the training to learn the design is quite costly. So there's some barriers there. From an oversight perspective, many people may ask why maybe code officials don't look for that. And I I am a code official. Their point of view or their vantage point, they're looking for equipment safety. So they're just looking to make sure that the equipment doesn't hurt anybody. So they're not trained to evaluate that. So it's a lack of training, a lack of availability of training, and then it's also poor oversight.
Yeah, thank you. Interesting to get the code official perspective as well. Like what priorities what you all are checking versus maybe some of the education being received by people starting out the profession or in the contractor space. Kind of to follow up on that, if a lot of homes then have oversized furnaces, or maybe an undersized ductwork, what would be some of the key design considerations contractors should focus on when installing heat pumps?
So if we're going to do a heat pump retrofit, if I was going to come to your place, the first thing we would do is do a load calc. The load calculation per manual J is going to have me evaluate your building shell. I put physical features of your home, such as the dimensions, the volume, the type of insulation you have, how much, how many people live there, how many pets, how many plants. We put a detailed survey of data into a software program and it gives us BTUs and it tells us how big or small your heating and cooling system needs to be. Um, if that process is skipped, nothing else will be right. So that's first and foremost. And then you have to work with your customer to understand their goals. If they're going to go all electric and they want to use a heat pump to totally support their structure, oftentimes there's going to be a bigger airflow requirement. Then I also have to evaluate the duct system to see if it can handle that. And if not, propose a duct modification inside the work scope.
Thank you. I also kind of enjoyed at the beginning of your presentation you sharing about some of the common myths or maybe misunderstandings of heat pumps. And I know there's such a big topic right now. So you mentioned that a lot of people think or have heard that heat pumps don't really work in cold climates. And of course, we're in the Southeast, but it can get cold here. Thinking of my family, in the mountains of North Carolina and Virginia. What one, like, why do we think this misunderstanding happened or is still present, and then what makes these new cold climate systems different from some of the older models and more applicable or helpful in cold climates?
Sure. So heat pumps had two rated temperatures that they were tested at, and that was 47 to 17 degrees. And as a older, I'll talk about a legacy heat pump. As it operated and it dropped in temperature, its capacity dropped. And when its capacity dropped, it will run continuously and not satisfy your thermostat. So as a result, your bill will skyrocket. If you Heat pump adoption was attempted before in the past, and when heat pumps went in, because those factors were not quite understood, a lot of customers had some really bad experiences due to high bills and not being comfortable. So the heat pump technology was a part of it too, but also understanding that the heat pump capacity did fall off at cold temperatures. Now, the heat pumps, because of that compressor being an inverter, I can control the speed precisely. The heat exchangers are well designed, and then I can control other features precisely, such as the airflow on the outdoor unit and indoor unit. I can modulate and control every aspect of the heat pump and totally deliver comfort. And they're designed to go all the way down to really extreme temperatures. So a heat pump now, compared to the past, it can deliver its total capacity, and it doesn't have that stark, drastic drop off in colder weather.
Thank you. I'm thinking back to even some of our SEEA coworkers were trying to take advantage of some of the tax incentives going on right now. Have you found that that's been a pretty big driver in your experience for kind of heat pump sales? Um, I suppose, yeah, with some of this funding, of course, the status can be a little up in the air right now. Like, what kind of opportunities do you see for contractors? And yeah, what have been some effective ways to communicate with homeowners about this technology?
That's an absolutely great question. So, um, heat pumps are incentivized. The tax credits expire this year due to the recent legislation. So there's no reason to delay. As a in our contracting business, the problem is awareness. Not a lot of customers are aware that there are incentives that are available and that those incentives have timelines on them. So if we're able to communicate the urgency of making those decisions, because who doesn't want to save 2,000 bucks, right? If I especially if I had to replace my system, if that was something I had to do, and I had to do it anyway, if I did it now rather than later, I'm going to miss out on that incentive, and who knows if it'll come back or not. So, just communicating and making customers aware is probably the best course of action.
Thank you. And then perhaps you mentioned this, but what's the typical kind of heat pump longevity, maybe in comparison to a different system? I'm, yeah, curious to hear how that ranks with some other options.
Sure. ASHRAE, American Society of Heating, Refrigeration, and Air Conditioning Engineers, they have a chart that's a lifetime life equipment lifetime expectancy chart. Heat pumps, air conditioners, when properly installed and maintained properly, have a life cycle of 15 years. 15 years. So if it's installed properly and maintained, you can get some good long longevity out of it. Uh, However, if you don't have those design fundamentals behind you and you put it in that's too large or something like that, you're going to shorten that lifetime of that equipment for sure.
Right. What is some of the maintenance required?
Uh, Identifying, monitoring issues such as loss of refrigerant, cleaning the heat exchanger surfaces, simple things like keeping your filter clean, that can't be overstated. Those type of things, even though mundane and simple, often get overlooked and they cause issues.
Yeah, that makes sense. Um, And then maybe I've got one more question for you, Brynn. You said that dual fuel systems were your favorite. Could you tell me a little bit more about why that is?
I like dual fuel in our particular region because our electric rates are high compared to our gas. So if you were to put an all electric system in our region at 20 cents, 23 cents a kilowatt hour, that could be a huge financial burden to have that bill month in and month out for customers, which doesn't help climate emissions if you can't afford to have the heat pump. So the dual fuel option, which is my favorite, and the reason why it's my favorite, I believe electrification is the right thing to do. I believe the rates make it sometimes impractical, especially for moderate income families. So as a result, if I set up dual fuel, I can run my heat pump up to a point, and I can calculate at what temperature it's going to be more cost effective to run my heat pump versus my furnace. And if I do that, I can still get most of my year covered by the heat pump and go electrification. And then I have the comfort of knowing I have a gas backup if I need it. So that's uh that's my silver bullet to meet people's climate goals, meet their budget, um, and then give them some assurance that if the heat pump has a malfunction, they still have a backup.
Yeah, I could see how that could be a pretty good
Yeah,
like a sales point there. This
yeah.
is going to help keep you comfortable. Also, you have these goals for related to the climate, and in any event, there is a backup system if needed. So yeah, thank you for sharing that perspective.
No
I
problem. I think Cody has his have their hand up.
Oh, perfect. Sorry, I missed you, Cody. If you're able to speak, please do. Otherwise, please drop your question in the chat or the Q&A. Give him a moment if you're typing. Oh, there we go.
Oh,
Sorry.
okay.
No worries. Wonderful. Well, yeah, thank you so much, Brynn. I think that's all the questions we have. So we will begin wrapping up. I want to share my screen really quick to pull up our survey. Wonderful. Yeah. As we mentioned at the top, this is recorded, and so we'll send this recording out to all of our registrants as well as the slides. We've got this survey here. It's the first QR code. We'd love to hear your feedback. And then also I have to plug a SEEA event. We've got our 2025 Southeast Summit happening in Atlanta, November 17th through 19th. Brynn, correct me if I'm wrong. Are you going to be joining us?
That's the plan.
That's the plan.
Yep.
So come see us at Summit and follow up with Brynn on what he was able to present to us today. So yeah, we appreciate everybody's time, especially appreciate your time, Brynn. Thank you very much. Everybody enjoy the rest of your day.
No problem. Take care.
Mm-hmm.